Okay, let's now look at a few examples of how to apply some of those definitions that I gave you. So let's start with an example like just let's take the function y equals sine x. And that's a terrible axis. Sorry, these graphs are not going to be that great. So here's sine function. Okay, so I might ask, well, where does the sine have an absolute maximum? Okay. In other words, where is its highest y value? Well, you notice here, and this is one thing that makes this example immediately interesting, it has a number of places where it has that highest y value. So the highest y value is at 1, and it achieves that at a lot of different places. So it achieves that at pi over 2, here's pi, 2 pi, this place is actually 5 pi over 2. Another place it achieves it is negative 3 pi over 2. So it has absolute maxes at an infinite number of places actually. So like pi over 2, 5 pi over 2, 9 pi over 2 is going to be the next one. It has negative 3 pi over 2, negative 7 pi over 2. So it has a lot of absolute maxima, but it has one maximum value. So the maximum value is the y value, and that maximum value is 1. Now if I ask, well, what about an absolute minimum? Where do those occur? There are, as before, there's an infinite number of those as well. So one of those is happening here at 3 pi over 2, another one is happening at negative pi over 2, so we have a number of these. 3 pi over 2, next one's actually going to be 7 pi over 2, negative pi over 2. But again, just like with the maximum value, the minimum value, there's only going to be one minimum value. That's the y value where it's lowest, and that y value is negative 1. Okay. Now if I say where are the local maxima are actually right here where the absolute maxima are. So if you take like pi over 2 for instance, and you just look at a region around it, this is the highest point in that region, so it's a local maximum. So our absolute maxima are actually local maxima here as well. Now you might think, so does that always happen? The answer is no, but we'll look at an example where something weird like that happens a little later. So let's delete that there. Let's look at another example here. So let's maybe graph. Let's take the example of x squared, but let's restrict where we are. So let's go from 0 to 2. So we're going to take the x squared function, which would normally look like this, but we're just going to go from 0 to 2. It's going to look something like that. Okay. So again, let's ask, well, where does this have its largest value? So where is its absolute maximum? Well, the absolute maximum, the x value, is at, you can kind of see from the picture, it's at x equals 2, and the maximum value is 4, because 2 squared is 4. The absolute minimum, the smallest value that this takes on, is at 0, and the minimum value is y equals 0. So if somebody asks me, well, what are the extreme values? The extreme values are the minimum value and the maximum value. So here the extreme values would be 0 and 4. It's kind of like the lowest and the highest that the function gets. What's strange about this example is that if you ask me about a local max, what's weird about this example is there actually isn't a local max here. So a local max, let's take you would probably guess that this would be our candidate for a local max right here. Now if I take an open interval around this and look at the function on that interval, it's true this point is the highest point on the left side, but if you look on the right side there's no function here, which means there's nothing to compare, so I can't make a statement that this is the highest point in this region because there's nothing else in the region. So there's actually no local max, which is kind of weird here. So we have an absolute max here that's not a local max. And in a similar way, if you ask me for a local min, there's going to be no local min either. So this is kind of strange. Let's maybe modify this again some here. So let's try another example. Let's take that same function x squared, but we're going to put it on a slightly different restriction here. Let's have it go from 0 to 4, but not including 0 or 4. I probably meant it'd be better to do 2 here, but we can do 4. We can work with this. So we're not including 0, we're not including 4, but we're taking everything in between. Okay. So now, if you ask me for the absolute maximum, what's interesting about this example is that this function never gets to a highest point. It gets as close as it possibly could, but it never actually achieves that highest point. So there is no place where it has a highest value. There's no absolute max here. And in a similar way, since this is open down here too, there's no absolute min. And as you can probably guess, if you ask for a local max or a local min, there's also going to be none. So this function has nothing. There's nothing in terms of extreme values one way or the other that would help us. Okay, so it's possible to have no absolute max, no absolute min. You can actually have nothing. So that can kind of make things a little bit interesting. Okay. Let's maybe do 2 more examples. So let's just take x squared now with no restrictions. And of course my axes look terrible here. Alright, but there's x squared. Take a second, pause this video, and see if you can tell me what's the absolute max, what's the absolute min, are there any local maxes, are there any local mins? So just take a second and pause it. Okay, so if you paused it, let's see if what I'm going to put down here is what you would have said. So absolute max, there is no highest value, so this is going to be none. But the very lowest value that you get happens at x equals 0. And so then if we're talking about a local max, it turns out there's none of those either. But we do have a local min here. There's a local min at x equals 0, and that's because, again, if we take a neighborhood around this, this is the smallest point in there. So hopefully that was what you put down as you were looking at this. Okay, let's do one more example. This one's kind of a fun one. It looks simple, but it's actually kind of weird. Let's see what's going on here. Alright, so this last function, let's just take the constant function 2. So 1, 2. Draw our line there. Okay. So take a second and see if you can figure out where the absolute maxes, absolute mins, local maxes, and local mins. Just try pausing the video again and see if you can figure those out. Okay, let's take a look. So absolute max, where does this achieve its highest value? Well, its highest value, the max value, let's answer that first maybe. The max value is y equals 2. And where does it achieve that? Everywhere. So all x are absolute maxes. And, as you can probably guess now, all x's are going to give you absolute mins because the min value is also y equals 2. And in addition, everything is a local max and everything is a local min. Because if I take any point here and look at its value, let's call that c, it turns out f of c is bigger than or equal to, it's equal to, so it's bigger than or equal to every other f value. So it's a local max. It's also a local min because I can switch this because of the equality. Everything's equal here. So this is kind of also a weird example, but so you can have lots and lots and lots of absolute maxes and absolute mins. Okay, so the last section that I'm going to just give a short lecture on is just on a theorem called the extreme value theorem that talks about, well, when do we have absolute maxes? When do we have absolute mins? Is there anything that could guarantee us that we will have an absolute max or an absolute min?